Welcome back. Today we're going to be looking at the Unit 3 pink sheets. These are reasons to be used in geometric proofs. So here are some theorems, postulates, definitions that we will be using or referring back to when we are doing geometric proofs. So let's look at the first page of the pink sheets. We're going to reference this page when using segments and angles. So the first item that we'll be discussing is the segment addition postulate, which states that if B is between A and C, then AB plus BC is equal to AC. So this is what we talked about back in Unit 1. This is basically the part plus part is equal to a whole. So suppose that B is between A and C, which I'm going to draw. So you have a segment with endpoints A and C, and B is between those two endpoints. So we'll put B right here. So essentially what that's saying is you have a part plus part, which is the whole thing, and that's the segment addition postulate. Part plus part is equal to a whole. The next item that we'll be discussing is the definition of midpoint. If M is the midpoint of line segment AB, then line segment AM is congruent to line segment MB. But we also have to note that this is a definition. That means that it can go both ways. So whenever you have a definition on your pink sheet, you will be given a double-sided arrow just like this. That means the statement goes both ways. So the first way was if M is the midpoint of line segment AB, then line segment AM is congruent to line segment MB. But I can also say the other direction. If line segment AM is congruent to line segment MB, then M is the midpoint of line segment AB. And that's because midpoint is considered a definition. So if you have a definition in general, you will be seeing a double-sided arrow just like this. So let's write this down. This is called the biconditional arrow. Now, let's take a look at this again. If M is the midpoint of line segment AB, what is the result of that? Let me go ahead and illustrate with a picture. We know that we're dealing with line segment AB, so I'm going to draw that. So here's my line segment with endpoints A and B, and M is the midpoint, so it should be right here in the middle. Now what happens if M is the midpoint of line segment AB? Well, what's the meaning of midpoint? The midpoint is going to split this whole segment into two congruent halves, which will result into this. It's going to give me line segment AM congruent to line segment MB. So this segment here is congruent to this segment there. So that means I need to draw my tick marks. One tick mark for line segment AM and one tick mark for line segment MB. This is to tell the reader that line segment AM is congruent to line segment MB. So, in layman's term, part is equal to part. Now, the other direction. If line segment AM is congruent to line segment MB, what does that imply? Well, both of these two segments are congruent, and both of these segments carry the letter M. So that implies that M is the midpoint of line segment AB, and here is that picture that I drew. Now let's take a look at the angle addition postulate. The angle addition postulate states that if point B lies in the interior of angle ADC, then the measure of angle ADB plus the measure angle BDC is equal to the measure angle ADC. So I'm going to go ahead and draw angle ADC. So D is my vertex, and this is point A, and that's point C, so I have angle ADC. Now what I'm going to go ahead and do is draw point B, which lies in the interior of this particular angle. So then I can go ahead and draw this ray right there. Now, if point B lies in the interior of angle ADC, what's the result of that? Well, you're going to have a part plus part, which will give you the whole thing here. Okay, so the measure angle ADB, which is a part, plus the measure angle BDC, which is another part, is going to give you the whole thing, measure angle ADC. Now, what if you're given this scenario? If angle AOC is a straight angle and B is any point not on line AC, then the measure angle AOB plus the measure angle BOC is equal to 180 degrees. So I'm going to go ahead and draw angle AOC, which is a straight angle. Now, B is any point not on line AC. So I'm going to go ahead and draw a point right there and call that point B. And I'm going to go ahead and draw my ray. And O is the vertex because it's the middle letter. So you have a straight angle, and this picture resembles a linear pair. So from me drawing this picture, if angle AOC is a straight angle and B is any point not on line AC, what's the result of that? Well, the measure angle AOB plus the measure angle BOC is equal to 180 degrees. Allow me to use this opportunity to highlight. So the measure of angle AOB is right here, which is that part, that angle, plus the measure angle BOC, which is this angle. And if you add these two angles together, what are you going to get? You're going to get 180 degrees. which is usually the case whenever you have a straight angle or a linear pair. The definition of angle bisector. If ray OC bisects angle AOB, then angle AOC is congruent to angle COB. Again, with a definition, it goes both ways. I can also say if angle AOC is congruent to angle COB, then ray OC bisects angle AOB. So I'm going to go ahead and show you the first direction of this conditional. If ray OC bisects angle AOB, then angle AOC is congruent to angle COB. So I'm going to go ahead and draw angle AOB. I'm going to go ahead and draw a ray that looks like it's bisecting angle AOB. So this will be point C. Now look, angle AOB is being bisected by ray OC. If ray OC bisects angle AOB, then what's the result of that? The result would be angle AOC is congruent to angle COB. This is what we call the angle bisector, which is essentially the midpoint of angles. So angle AOC is congruent to angle COB, and I'm going to draw one arc here and one arc there to indicate that those two angles are congruent to each other. Now remember, this is still a definition. I can say if angle AOC is congruent to angle COB, what's the result of that? Well, here's angle AOC, and it's congruent to angle COB, which implies that there is an angle bisector, which is ray OC. So the statement could be read, if angle AOC is congruent to angle COB, then ray OC bisects angle AOB. Definition of congruence. Now suppose that you're given two segments that are congruent to each other. For instance, line segment DE is congruent to line segment FG. Then it implies that those two segments are equal to each other. So we say that the measure of DE is equal to the measure of FG. Or if you're given two angles that are congruent to each other, for instance, angle R is congruent to angle S, then it implies that the measure of angle R is equal to the measure of angle S. Now here's what's happening. As you can see, on the left-hand side of this statement, we see the congruent symbols. Whenever you see the congruent symbol, we are in the language of geometry. We are dealing with shapes. On the right-hand side, we see equal signs. That means we are in the language of algebra. So that means that this shape has to be congruent to this shape. For these two angles here, we can say that this shape is congruent to that shape. All in the language of geometry. So I'm going to go ahead and show you with an example here, using these two segments. So line segment DE and here's line segment FG. These two segments are congruent to each other, and how do I indicate congruency? I'm going to use tick marks. So one tick mark here and one tick mark there. So these two segments here are congruent to each other, and we're just involving shapes, no numbers. Now, if we want to talk about numbers, we can look at the right-hand side. The right-hand side of this statement deals with equal signs. And whenever you see an equal sign, you are dealing with the language of algebra. The language of algebra deals with numbers and measures. So if we look at these two segments here, the measure of this segment is equal to the measure of that segment. Or if we look at these two angles here, the measure of this angle is equal to the measure of that angle. So here's segment DE. And the measure of this segment will be 3 centimeters. And here's segment FG. So this will also be 3 centimeters. So the measure of this segment is equal to the measure of that segment, which is DE equals FG. We are dealing with numbers, so this is all in the language of algebra. It's important to note that you could be switching from the language of geometry to the language of algebra because of definition of congruence. Or you could be switching from the language of algebra to the language of geometry, again, by the definition of congruence. It's a biconditional statement, so it goes both ways. I just want to demonstrate my point about the language of geometry and the language of algebra once more. We can see that these two segments are congruent to each other, and they are equal to each other in terms of measurement. So if I say 3 is congruent to 3, that sounds odd, right? Remember, the congruent symbol deals with shapes, not necessarily numbers. So instead of saying 3 is congruent to 3, I should say 3 is equal to 3. That sounds much better because we are in the language of algebra. So this is wrong, and this is correct. So you're probably wondering why we're doing these pink sheets. Again, the reason why we're doing these pink sheets is because we're trying to get you ready for 2-column proofs. You are going to be justifying with a lot of these reasons. We're going to be using theorems, postulates, definitions in order to prove a statement. Let's move on to the next page here. Reference this page when using special pairs of angles. The vertical angles theorem states if two angles are vertical, then they are congruent. So I'm going to draw a picture. I'm going to go ahead and draw two straight lines that intersect each other and form an X. So because I drew this picture, we have 4 angles created. We have angle 1, angle 2, angle 3, and angle 4. Now remember, the angles across from each other are congruent. Angle 1 is congruent to angle 2, so I'll draw one arc here and one arc there. And angle 3 and angle 4 are congruent to each other, so I draw 2 arcs here and 2 arcs there. So using numbers and symbols, I will say that angle 1 is congruent to angle 2 due to the fact that they are vertical angles. And angle 3 is congruent to angle 4, again, by vertical angles. Definition of complementary angles. Now, this is a definition, so it's a biconditional. If two angles sum up to 90 degrees, then they are complementary angles, or if they are complementary angles, then two angles sum up to 90 degrees. So, I'm going to provide you some examples of complementary angles. Suppose I have angle A, and the measure of angle A is 20 degrees. And here's angle B. And the measure of angle B is 70 degrees. Or what if you have something like this? So these are two different types of complementary angles. One where these angles are not adjacent, they are not stuck together, but they do complement each other. These angles add up to 90 degrees. And over here, we have adjacent angles being involved, or to be specific, these angles are adjacent complementary angles, or in other words, these angles are stuck together. But we do know that these two angles add up to 90 degrees as well. So the measure of angle A is 20 degrees, and the measure of angle B is 70 degrees. 20 plus 70 is equal to 90. Therefore, these two angles are complementary. So I'm going to make a note. The measure of angle A plus the measure angle B equals 90 degrees. The example over here, we can see that these two angles add up to 90 degrees. So the measure of angle X, Y, W is 60 degrees, and the measure angle W, Y, Z is 30 degrees. 60 plus 30 is 90. So let's make a note. Measure angle X, Y, W plus the measure angle W, Y, Z is equal to 90 degrees. Definition of supplementary angles. Basically the same idea as definition of complementary angles, but instead of 90 degrees, we have 180 degrees. It is a definition, so the statement goes both ways. So if two angles sum up to 180 degrees, then they are supplementary angles. Or if they are supplementary angles, then the two angles sum up to 180 degrees. So I'm going to provide some examples. I'm going to draw two angles that are not adjacent to each other, but supplementary. And then I'm going to draw a picture of adjacent supplementary angles. But note, the adjacent supplementary angles is what we considered a linear pair. And we'll talk about that after I draw those pictures. Here's angle C, and the measure of angle C is 30 degrees, and I have angle D, which will say that the measure of angle D is 150 degrees. Now I'm going to go ahead and draw my straight angle over here. I'm going to call this point E, this point F, this point G, and this point over here, not on that line, H. Then I'm going to create a ray right over here. Now let's say the measure of angle EFH is 130 degrees. And the measure of angle HFG is 50 degrees. So over here, the non-adjacent angles, these angles do supplement each other because 30 plus 150 degrees gives you what? 180 degrees. So the measure of angle C plus the measure of angle D equals 180 degrees. Now looking at the adjacent supplementary angles example, you can see that this angle is 130 degrees and this angle over here is 50 degrees. So if you add these two angles together, you're going to get 180 degrees. So I'm going to make a note. The measure angle EFH plus the measure angle HFG equals 180 degrees. And this example over here, by the way, is what we call a linear pair. Awesome, and don't forget that this is a definition, so it goes both ways here. Let's go ahead and move on to linear pair. Now, the linear pair theorem states that if two angles form a linear pair, then they are supplementary angles. Basically, it's this example over here. So these two angles form a straight line, therefore a linear pair, and those angles add up to 180 degrees. These two angles are supplementary angles. If two angles form a linear pair, then they are supplementary angles. That's true. But if I were to state the converse of the linear pair theorem, if the angles are supplementary, then they form a linear pair. Is that true? So let me go ahead and write that. The converse, if two angles are supplementary, then they form a linear pair. Now the question here is the converse of the linear pair theorem true? If false, provide a counterexample. The converse is if two angles are supplementary, then they form a linear pair. So assume the hypothesis is true. Two angles are supplementary. If two angles are supplementary, does it strictly mean they form a linear pair? Well, these two angles over here are supplementary and they do form a linear pair. However, these two angles are also supplementary, but we can see that they are not adjacent to each other. Therefore, these two angles do not form a linear pair, and the converse is not true. This is my counterexample. So the converse is false. So know that the linear pair is not a biconditional statement. It only goes one way. If two angles form a linear pair, then they are supplementary angles. And that direction there is true.